our discussion of duality theory, which, as I said, is in section 4.2 of your textbook. And in doing so, we'll also cover certain elements of the last part of chapter 3, which we didn't touch upon. And once we finish this, the next lecture, we will discuss sensitivity analysis and the dual simplex method. Okay? And that will sort of wrap up our discussion of linear programming. I want to say a little bit about the midterm as well, but we'll probably wait till the end of the lecture so that if there are latecomers, we'll cover those people too. Just a reminder that there's a homework due tomorrow, and unfortunately there were a couple of little typos in the homework, so I don't think it affects anything seriously. So, if you've done work, you don't have to redo anything. But if you're puzzled by one or two parts of certain questions, it may be because there are little errors in subscripts and so on. Okay. So, and just to remind you what we were discussing, we were looking at this particular maximization problem, which we call the primal problem. And we are going to look at it in sort of symmetric form. So the maximization problem is always going to have less than equal to constraints and non-negative variables. And we saw last time how one can derive the dual using a certain motivation, which is one of finding upper bounds on this maximization problem. Okay? So recall that if you find any feasible solution to this linear program here, that will give you a lower bound. So if you find a feasible solution with value 10, then you know that the optimal solution to that problem, or the optimal value of that problem, is at least 10. Okay? However, to find upper bounds, which is like saying that no solution to this problem can have value more than 25. Okay? So to do something like that, we saw that that was a little more difficult and more intricate, and we were naturally led to considering this dual linear program over here, which is one of minimizing some bi times yi subject to these constraints. Okay? So the minimization problem will always involve greater than equal to constraints and non-negative variables. Okay? And this is what's called a symmetric form for linear programs, and it's not difficult to show that any linear programming problem can be converted to symmetric form. Okay, so I may even put in one or two homework problems for you. Okay. Maybe a part of a homework problem in this homework will involve converting a general linear programming problem into a symmetric form LP. Now, one of the nice things about all of this is that the discussion of duality becomes much more transparent in this setting. So for one thing, you don't have to remember all these rules that say how you convert. Okay, so there's a standard form for discussing duality. The other advantages will become clear as we go along today. Okay, so now what does that mean? One implication is that some of the results that we derive is going to be specific to this particular form of linear programs. Okay, and so you want to watch out when you sort of want to carry over these results to more general settings. You have to make some appropriate changes, and I will warn you when the time arises. By the way, you don't have to write down everything because I'm going to put this as a PDF on the home page. Okay? So don't worry too much about what's written here. So any linear program can be converted to the symmetric form, and duality discussion becomes much more simplified in this setting. And we are going to look at everything, all the results for this particular form. Okay? So let me quickly remind you of the set of results that we discussed last time. So the first result is if you have a primal feasible x and a dual feasible y, then the primal objective value is at most the dual objective value. Now, this was our motivation for deriving the dual linear program. So you could see this result as sort of capturing that motivation formally. And there's a simple proof of this. And here's what it is. So you start out by looking at the primal objective value associated with x, and you observe that that quantity is at most this. Okay? And to derive this inequality, you just make use of two things. You make use of the fact that y is dual feasible. Therefore, this quantity over here, underlined in green, is at least this quantity Cj. Okay? And you make use of the non-negativity of xj, so you get this. The next equality is just rewriting this term in a slightly different way. That's useful for the remaining inequality that we want to derive. And symmetric to this, we have an inequality like this that says that this quantity is at most the dual objective value. Okay? And there you make use of the primal feasibility of x and y being non-negative. Okay? So it's simple proof involving 3 steps that establishes what's called the weak duality theorem. Okay? Now, moving along, we said there's something called the strong duality theorem, which says the following, that if you have an optimal solution to the primal problem, okay, then the strong duality theorem asserts the following, that the dual problem also has an optimal solution, and the objective values are the same. Okay, so in other words, if you have any linear program which attains an optimal value, then so does the dual, and the dual LP has the same objective value as the primal LP. Okay? Now, by weak duality, this is sort of the best possible. There's no gap between the two. Okay? And I have not yet proved this result to you. Okay? But what we discussed last time was that if strong duality holds, then the chain of inequalities that we wrote down in the weak duality proof, all of those have to hold with equality. Okay. So if you put x star and y star, which are optimal solutions to the respective problems, then strong duality says the objective values are the same, and we derive a chain of inequalities for the weak duality theorem, which is sort of replaced here. And if strong duality has to hold, then this has to hold as an equation, and this has to hold as an equation. Okay. So these two are inequalities in the proof of the weak duality result. And then we just observe that if this has to hold, then whenever xj star is positive, okay, you better have Cj being equal to this quantity. Okay? Because we know that by dual feasibility, Cj is at most that quantity. And if xj star is positive, and if there's a strict inequality, then this quantity cannot possibly equal this quantity. Okay? Similarly, you have a set of conditions that are dual to that, which involve yi star and aij xj star. And if you work out the implications, what you end up with is the following. So either you have xj star to be 0, or you have that quantity satisfied as an equation. Okay? Similarly, either you have yi star equal to 0, or the corresponding primal constraint must be satisfied as an equation. So these are called complementary slackness conditions. And what we've just shown is that if strong duality holds, then the CS conditions must be satisfied. So if you take any pair of primal dual feasible solutions with the same objective value, then these conditions have to be true of those solutions. Okay? Any questions about any of this? This is just recalling developments from the previous lecture. Okay. Now, I just want you to notice that all of this works in reverse as well. That if the CS conditions are satisfied, then these two things have to be equal also. Okay? So in other words, if I give you a primal feasible solution, X, and a dual feasible solution, Y, such that these two solutions satisfy the complementary slackness conditions. Okay? Meaning, if some component of X is strictly positive, then the corresponding dual constraint is satisfied as an equality, and vice versa. If some component of Y is strictly positive, the corresponding primal constraint is satisfied as an equality. Okay? If those conditions are satisfied, then the exact same argument worked in reverse will establish that the primal and the dual objective values are the same. Okay? The second implication that's written down there is just what we prove. Right? That we start with two solutions whose values are identical, then the CS conditions have to be satisfied. Okay? The assumption, of course, is that X star and Y star are feasible solutions to the primal and dual problems, respectively. Okay? Let's actually try to understand what these conditions mean in a little bit more detail. Okay? So here again are the primal and dual problems. Now what I'm going to do is I'm going to convert them to standard form. Okay? So to convert this problem, the maximization one, into standard form, I have to add some slacks, SI. Okay? And to convert the minimization problem into standard form, I actually have to subtract Wj. So I think I made an error here. Okay. So this is just, so the problems that are written down here are exactly the same primal dual pair of problems, except that I've now rewritten things in standard form. And I've made a whole bunch of errors, so let me fix all of those. Okay. Okay. Now, for the primal problem, I introduce slack variables, which are SIs, and I say that the ith constraint now reads summation Aij xj plus the slack equals Bi. Okay. Or in other words, Si is going to represent the difference between Bi and the amount of resource I that I actually consume in my solution X. Okay. So Si is the slack of resource I. Similarly, Wj is going to be the surplus of resource J in the dual problem. Okay? So we've just rewritten the primal dual pair of problems in standard form. So here my variables in the primal are X and S. The variables in the dual are Y's and W's. Now, in terms of the new variables, what does the complementary slackness condition say? So if Xi is strictly positive, then what must be true? I mean, if Xj is strictly positive, then what must be true? If Xj is strictly positive, then you want the corresponding constraint in the dual to be satisfied as an equality. Okay. So which means you want Aij Yi to equal Cj. Okay. That's exactly what the CS condition says. And if Aij Yi, if that summation equals Cj, then what must be true of Wj? Wj should be 0. Okay. So the interpretation of the complementary slackness conditions is that if xj is strictly positive, then wj has to be 0. Okay. Similarly, if yi is strictly positive, then si has to be 0. So it's just saying that certain pairs of constraints, the products of certain variables have to be 0. Okay. So really another reading of the CS conditions is that either xj star is 0 or the wj star is 0. Okay. Now both of them could be 0, of course, but at least one of them has to be 0. That's what the CS conditions say. Okay. Likewise for the y's and the s's. So you can sort of see that there's a natural relationship between, let me go back up a little bit, there's a natural relationship between the slacks of one problem and the variables of the other. Okay? The surplus of one problem and the variables of the other. So you can see that xj, which is the jth variable of the primal problem, is somehow associated with wj, which is the surplus, jth surplus variable of the dual problem. Okay. And all this is saying is either you don't produce any amount of product j at all originally, or if you make a positive amount of product j, then it better be that the slack of the corresponding variable, surplus variable in the dual problem is 0. Okay. Any questions about this? This is just rewriting the CS conditions in a slightly different way. Okay. Now, why is this important? Well, for now, just keep in mind that there's a natural relationship between the original variables of one problem and the slack or surplus of the other. Okay? And we are going to exploit this relationship in designing a new algorithm for linear programming, or looking at the algorithm for linear programming in a slightly different way. Okay, so let's go on. Let me quickly record all the implications of what we did. Okay? So I've just written down a whole bunch of conditions. I still have not proved to you that the strong duality result holds, but we're going to look at that in a moment. But other than that, we have sort of written down a whole bunch of things, proved some results, and I just want to record all the implications. Okay? So the first implication is that if I give you a primal feasible x and a dual feasible y, and they happen to have the same value, then they are optimal for their respective problems. Okay? So to prove this, the only thing you need is weak duality. Okay? So by weak duality, Zp of x is at most Zd of y, so that must be Zd. Okay. Therefore, if you find an x such that Zp of x is actually equal to Zd of y, then you know that there cannot be a better solution to the primal problem. Okay? Because the fact that you found a feasible solution to the dual with this value means that this value is an upper bound on the primal objective value. Okay? So imagine that this quantity is 25. What that is saying is no solution to the primal problem can have value more than 25. Okay? So if you find any solution with value 25, that has to be an optimal solution. And do this reasoning with the primal and dual interchange, and you prove that y has to be optimal for the dual problem as well. So this is sort of the easiest implication, and the proof just uses weak duality. Okay. Now, second implication is the following. If you have a primal feasible x and a dual feasible y, and if the xy pair satisfies the complementary slackness condition, then x and y are optimal for the respective problems. Okay? So why is this true? Very good. So because the CS conditions are satisfied, that means Zp of x has to be equal to Zd of y. And because x is feasible for the primal, y is feasible for the dual, and Zp of x equals Zd of y, go back to the first implication and you derive the optimality. Okay? Yes?
Yeah, Professor, I'm sorry. About the CS condition, we talked about Cj equals sigma of ai to yi, but we did not really talk about those kind of conditions that xj is zero. And I mean, if xj is zero, dtx is zero, and dy is zero.
No. So when we say that the CS conditions are satisfied, it is for each component. Okay. So when I say xj is 0, it means just xj is 0, not x1 through xn. Okay. So the CS conditions say that either a particular, okay, so you look at any component of x. If it is 0, then it doesn't tell you anything. If it is strictly positive, then it says that the corresponding dual constraint has to be satisfied as an equality. Okay.
And what does that strictly positive?
Strictly positive, right? If it is bigger than 0. So let me actually explain this in a slightly. I just want to make sure that this is not confusing. It's a simple point, but let me expand on it anyway. So let's actually look at this example that we have. Okay. So we wrote down a set of primal dual pair last time. So maximize 4x1 plus x2 plus 3x3. x1 plus 4x2 is at most 1. 3x1 minus x2 plus x3 most 3. x1, x2, x3 non-negative. Okay? And the dual for this, which we also wrote down last time, was minimize y1 plus 3y2. y1 plus 3y2 is at least 4. 4y1 minus y2 is at least 1. y2 is at least 3. Okay. Now, let's actually write down the CS conditions so that you see explicitly what it is in an example. Okay. So the CS conditions say the following. x1 times 4 minus y1 minus 3y2 equal to 0. Okay. x2 times 1 minus 4y1 plus y2 equal to 0. x3 times 3 minus y2 equal to 0. This is just another way of saying either x1 is 0 or 4 equals y1 plus 3y2. So either this variable has 0 value, or the constraint of which it is the dual variable. Okay, so x1 is associated with this constraint. That constraint is satisfied as an equation. So this can also be written as, this is equivalent to x1 equal to 0 or y1 plus 3y2 equal to 4. Okay. Now we know that y1 plus 3y2 it will always be at least 4. Okay. So this is merely saying that if x1 is strictly positive, meaning x1 is bigger than 0, then this constraint has to be satisfied as an equality at an optimal solution. All of this assumes that these two problems have optimal solutions, and the optimal solutions have to satisfy these conditions. Okay? So this is one set of CS conditions, and the other set of CS conditions are the exact analog, right? So you have y1 times yeah, I can just write it anywhere, like x1 plus 4 x2 minus 1 equal to 0. Similarly, y2 times 3x1 minus x2 plus x3 equal to 0. Okay? Is everyone comfortable with what these conditions are saying? Very good. Yes? So, these are not, there's no mystery to these conditions. This is exactly what it is saying. Okay? Now, what I pointed out a little earlier was that, we derive the CS conditions in this way. We said either, we had a certain pair of terms. So let me go back to that. So if you go to this proof of weak duality, okay, so those were the expressions, the chain of inequalities involved in proving the weak duality result. Okay. Now, if this quantity, Cj, Xj summation, equals this quantity, which is a summation of Bi, Yi. So for these two things, so for this one and this one to be equal, all of these have to be satisfied as equalities. Okay? So this quantity has to equal this. So this, instead of this, it has to be this has to be satisfied as an equation, and similarly this has to be satisfied as an equation. Okay? So if you find x and y having the same objective value, then this quantity equals this quantity, and therefore these less than equal to signs are all actually equal to for that particular pair of xy solutions. Okay? And now let's examine the first equation that we have. Okay? So if this has to be satisfied as an equality, then it must be that Cj equals this quantity underlined in green. Okay? Of course, it doesn't always have to be equal. If xj happens to be 0, then it really doesn't matter. Then both of those terms evaluate to 0. So in that case, it really doesn't matter. But whenever xj is strictly positive, you must have Cj equal to this quantity underlined in green. Okay? That's exactly what this condition says. Okay? That whenever x1 is positive, so that means this is not satisfied, then you must have this satisfied. Okay? Which is the same as saying that the product of x1 and this quantity should be 0. Okay? But this quantity is just the surplus or negative of the surplus. It doesn't matter what the sign is. Okay? And therefore, I can rewrite it yet another way by saying this is same as saying x1 times w1 equal to 0. Okay? Where w1 is the difference between these two quantities. Actually, the way I have written things here, it's actually x1 times negative w1 equal to 0, but it doesn't really matter. Okay? Is all of that clear? Okay. If there are questions, please stop. Yes. No, so all I'm saying is if you have x and y such that summation cj xj equals summation bi yi. Suppose you have an x and y satisfying that, then these inequalities that I wrote down are true for every feasible pair of x and y. Okay. So the chain of inequalities that I wrote down are valid for every feasible x and y. So if x is feasible for the primal and y is feasible for the dual, then whatever is displayed there is valid with the less than equal to sign. No, not just for optimal. This is for every feasible solution, right? So if you go back and look at this, so if you look at this quantity summation cj xj, if I tell you that x is feasible for the primal and y is feasible for the dual, then this inequality holds. Okay? Why is that? Well, if y is dual feasible, then cj has to be at most this quantity underlined in green. That's the dual constraint, right? That's the jth constraint of the dual problem. And if x is primal feasible, then xj is non-negative. And therefore, the first inequality is valid. The second is just rewriting this expression in a slightly different way. It's just interchanging the summation. And the third is valid by a similar reason that I used for the first. Okay? So this is valid for every pair of x and y, such that x is primal feasible and y is dual feasible. Now, suppose you find x and y. I don't know whether they're optimal or not. I just know that x is feasible for the primal, y is feasible for the dual, and they happen to have the same objective value. Okay? That means the term that's here, this is equal to this. This is what you're telling me. And I just want to understand the implications of that. If these two things are equal, then this must be equal to this, and this must be equal to this. Okay. And if for these two terms to be equal, whenever xj is strictly positive, then cj has to equal that quantity. Okay. Because if it is strictly less, then you have one term strictly less, and every other term at least as much. So you cannot have equality. Yes?
I don't understand why the first line in the equation implies that we have cj equal the sum of I, because cj can be negative. So if I have a sum of positive numbers that is equal to 0, I understand that this number is 0. But here, if you do the difference, you might have negative numbers in it. Maybe.
That's okay. So the only thing, so remember that cj could be negative, okay? But remember that cj is always going to be at most summation aij yi, okay? because that's the dual feasibility. And therefore, you just need the non-negativity of the x's for that inequality to hold. And every term, the jth term on the left-hand side, is dominated by the jth term on the right. Okay? And therefore, for them to all add up to the same, every term has to be equal. Okay, so once again, because every term is every term on the left is at least as much as the corresponding term on the right. For you to have an equation, every term on the left should equal every term on the right. That's the only way you can have equality. Okay? And for every term to be equal, you must have either Cj equal to this quantity underlined in green, or you must have xj to be 0. Okay? Because if xj is 0, then the contribution of that term is 0, regardless of the value of Cj. So it really doesn't matter. But if xj is bigger than 0, then Cj has to equal that quantity underlined in green. Okay. Yes?
The thing that I'm confused here is that if you pick like x1, x2, x3, then those be all zeros, the like CS condition still holds, right?
Yes, you can pick all the x's and all the y's to be 0. The CS conditions hold. Notice that I am not telling you that if the CS conditions are satisfied, you are at an optimal solution. All I'm saying is if the CS conditions are satisfied and the y's and the x's you have are feasible for the respective problems, then you have an optimal solution. So let's actually examine your suggestion. Certainly x1, x2, x3, all 0 is feasible for this problem, but y1, y2 being 0 is infeasible. Okay? So it doesn't say anything. Okay? That's good. Okay? Yes.
Before you were relating the relationship between variable number 1 of the particle and then with the slack of it, how do you show that necessarily? How are you showing that this is the slack of the other door?
So when I convert this, so this is the same as y1 plus 3y2 minus w1 equal to 4. Okay? So w1 is exactly this quantity, or the negative of that quantity. Okay? Anything else? Okay, so let me actually follow up on a point that you just made. Okay? And let's now see how maybe we can use the CS conditions to do something reasonable. So let's see. Okay? So in the previous lecture, we had a feasible solution to this problem with value 10. So I think we said consider y1 equals 1 and y2 equals 3. Okay? And this satisfies all of the constraints. And so y is dual feasible, and ZD of y equals 10. Okay. Now, can we use this to actually, suppose we suspect that this is the best possible. Okay. Can we sort of use these CS conditions to figure out a primal solution? Okay. So let's see what happens. If y1 is 1, then what do I have? This condition says whenever y1 is 1, then the corresponding, y1 1 is bigger than 0. So y1 equals 1 implies x1 plus 4x2 equals 1. Okay. Now notice that we have dual feasibility. Okay. We want to work with the CS conditions and find an x. So how can you conclude that this is optimal? Well, for one thing, you should be able to find an x uniquely, or you should be able to find some x, and that x has to be feasible. Okay. If it is feasible, it will have the same objective value as 10, because whenever the CS conditions are satisfied, the primal and the dual objectives are the same. So for instance, if you take the all zero solution, the primal objective value is 0, the dual objective value is 0. So it's clear that, okay, but then the all zero is invalid because you don't have feasibility for the dual. Okay? So whenever you have a dual feasible solution, if you use the equations to find a solution x that happens to be feasible for the primal, then because the CS conditions are satisfied and you have feasible solutions, you have optimal solutions. Okay? So y1 is 1, then the CS condition implies that this must be true. Okay? Similarly, y2 being 3 implies 3x1 minus x2 plus x3 equals 3. Okay. Is everyone happy with this? Now, what else do we know from the CS conditions? Now, observe that this quantity, y1 plus 3y2, for this set of values is actually 10. Okay. So if this constraint is satisfied as a strict inequality, then what must be true? x1 has to be 0. Okay. So y1 plus 3y2 is 10, which is bigger than 4, and this implies x1 must be 0. Okay. So we have x1 being 0, and from the first equation, x2 has to be 1 over 4. Okay, and the second equation, x3 must be 3 plus a quarter, okay, which is 13 over 4. Okay. So does everyone understand how we got this x? Okay. We just used the CS conditions, looked at all the implications that we have, and we found an x.
Why you say like 10 is larger than like 4 and then...
So I just want you to observe that for this particular y1 plus 3y2 is greater than or equal to 4. I mean, it's always greater than or equal to 4, but it's strictly bigger than 4. Therefore, the corresponding x1 has to be 0. Okay, so let's go back to this condition. What does this condition say? But the thing in parentheses is not 0. That's what we just saw. Okay. It's okay. I mean, the first time is always like this. But, okay. So all we did, we had some candidate solution y. And we just worked out the implication. We used the CS conditions and we figured out some x. Okay. Now, is this x feasible for the primal? Well, obviously it satisfies the constraints, right? Because we used the constraints to derive the x in the first place. So the only way it could be infeasible is if it gave you something negative, but it didn't. So you have a non-negative solution x. Therefore, this just shows that the x that you find is optimal for the primal problem, and the y that you started with is optimal for the dual problem. Okay? So you didn't do any work, right, apart from just checking these implications. Okay? So x is feasible. Now, once you know that x is feasible, you don't even have to check its objective value. It will have to be 10. So we had some candidate solution last time, which was 0, x1, 0, x2, 0, and x3 was 3. And that isn't optimal. This is. Okay? So I'd be happy to answer any other questions you may have about this. Yes?
What's the conduit of non-duality called again? When dt is y equals to ddx, then both the x and y are optimal in the combination 1, 2, 3.
So when zp of x equals zd of y, and x and y happen to be feasible, then they have to be optimal. There is no name for this. This is just an implication of weak duality. Any questions about this development? Now, can you always do this? In other words, will this exercise always give you a unique x? It's not clear, right? So for instance, so is everyone comfortable with this? Okay. Now suppose I change this to 10. Okay. So therefore, okay. Suppose I started with that pair of problems. Okay. Then what happens? Well, my y is still feasible for the dual. Okay. Do you think, knowing that for the previous problem this was an optimal solution, what is an optimal solution to the dual? So remember that before we had, was this 4? This is 4. Now I'm getting rid of this, and I'm saying y1 plus 3y2 should be at least 10. Okay. So first question, if I do this, is my optimal cost going to increase or decrease? Is zd of y going to go up or go down? It cannot go down, right? You take any solution that's feasible for this new problem. Okay. So anything for which this inequality is satisfied, that solution will also satisfy this inequality. Okay. So if you find a solution with value 7 for this new problem, then the old problem will have value 7, or possibly better, meaning smaller. Okay. So certainly, when I increase this right-hand side in a minimization problem, the optimal zd of y may go up, or it may stay the same. It certainly cannot go down. Everyone happy with that? Okay. Now, that says that this solution is still optimal because this is optimal for the original problem and it is feasible for this new problem. So certainly you cannot do any better than 10, right? And here's a solution with value 10, with cost 10. So this is still optimal for the new problem. Okay? But when you do the CS conditions, what do you get? So you would get these two things, but you don't get this implication, right? You cannot infer that this is true. Of course, you could say, okay, let me try taking x1 equal to 0, and then you will figure this out, and this is optimal for the primal as well. Okay? But you have to try. You don't have this guaranteed. So we cannot make this inference, and therefore we certainly won't determine a unique x. These conditions will not give you one particular x value. So this method is not always, is not going to work always. Certain things have to be true. Exactly what will become clear after you do your homework. Yes?
What is the sequence of the various outputs supply 1, supply CS? So
these are true for the same reason that they were true before. That if some y is strictly positive, then the corresponding constraint in the dual of that problem, which is the primal, has to be satisfied as an equation. Okay. So it's true from this constraint over here. Now what happens is that the first condition now becomes x1 times 10 minus y1 minus 3y2, and your solution to the dual problem, this solution, sets the term in the parentheses to 0. Therefore, you don't know what x1 should be. x1 could be 0, it could be positive, but you don't know. Whereas in the previous case, this was strictly positive, so you could infer that x1 had to be 0. Okay? So the summary is that in certain cases, the CS conditions will determine a unique solution. Okay? That's the first example we saw. And in certain cases, it won't determine a unique solution. And so sometimes, if you suspect that a certain solution is optimal, you could invoke the CS conditions, argue that it results in a unique solution which is feasible, and therefore prove optimality. Okay? That's what we did for this solution with the original constraint. But that trick may not always work. And there's a little homework problem in your next homework that will sort of teach you exactly when this will work. Okay? Questions about this? So does everyone understand these conditions better now? Exactly what they say. Okay. Okay, so let's continue with our implications. Okay. So this is where we were, right? That the CS conditions say that either a certain variable is 0 or the corresponding slack or surplus is 0. Okay? And of course, both of them could be 0, as in the second example that we saw. Okay? So we're discussing the second implication, that if you have a primal feasible solution and a dual feasible solution, and they happen to satisfy the CS conditions, then they are primal optimal and dual optimal respectively. And the proof is that if they satisfy the CS conditions and feasibility, that implies that ZP of X and ZD of Y are the same, and therefore we're done. Okay? Let's look at yet another implication, which is sort of straightforward. If the primal problem is unbounded, then the dual problem must be infeasible. Okay? And this is true by weak duality. So why? Well, if the dual problem were feasible, let's say that there was a solution to the dual problem with value 1 million, then that immediately puts a bound on the primal objective value. The primal cannot be bigger than 1 million. Therefore, if you know that your primal problem is unbounded, then the dual problem cannot have any feasible solution. It's just weak duality. So that's what's written down here. Okay. Okay. Let's actually now look at this example that we have. Okay. This example is written down here as well. Let me get rid of all the blues. And what I want you to observe is the following. So first of all, so in the remaining 10 minutes or so, what I want to do is look at the dictionaries associated with these two problems, the primal and the dual. And I want to observe that the dictionaries satisfy a nice relationship. Okay. So, of course, I can write down the initial dictionary very easily for the primal problem, and that's exactly this. Okay. So of course, unfortunately, you can't see the problem there, but you can see it here. Okay. So all I've done is taken S1 and S2, the two slacks, as my initial basic variables, and I do the obvious thing. So I get an initial dictionary. Now for the dual problem is written here. Okay. But remember that we do dictionaries only for maximization problems with equality constraints. Okay. So the first thing I want to do is to convert the dual into a maximization problem with less than equal to constraints. So how do I do that? Well, minimizing y1 plus 3y2 is the same as maximizing the negative of that. And I multiply all the constraints by -1, I get those constraints. Okay? And now I can write down the initial dictionary fairly easily, which is that I'm going to use W's as slack variables for these three constraints, and I get the following dictionary. Okay. So I have W1 to be -4 plus y1 plus 3y2. Okay. So in exactly the same way that we wrote down the dictionary for the primal problem, I'm writing down the dictionary for the dual problem. Okay. Which, remember, once again, that we are still maximizing, okay, but we are maximizing this objective function, -y1 minus 3y2. Okay? Now, what is the problem with this dictionary? For one thing, it's infeasible, right? It says W1 is -4, W2 is -1, and so on. Okay? Does everyone agree that this is infeasible? But what is nice about this dictionary? Suppose I do allow for W's to be negative, meaning, let's say W1 could be as small as -4, and W2 could be as small as -1, and W3 could be as small as -3. Suppose this were feasible. Okay. But Y1 and Y2 had to be still non-negative. Okay. Suppose this were feasible, suppose this were allowed, then if this were feasible, then this would be an optimal dictionary, because every variable has a negative coefficient. Okay. So what is nice about this dictionary is that it satisfies the optimality conditions that we have for stopping the simplex method. Okay. However, it's infeasible. Now, notice the symmetry, that if you look at the dictionary in green, it is feasible, but does not satisfy the optimality conditions. Okay. Whereas the red dictionary is infeasible, but satisfies the optimality conditions. Okay. Any other similarities between these two dictionaries? Let's look at the last row of the green dictionary. What are the coefficients? 4, 1, and 3. Okay. If you look at the first column of the red dictionary, you have 4, 1, and 3 with a negative sign. Okay. And actually, that's true for every row. So, look at the second column of the green dictionary. You have -1, -3, and 4, the X1 column. Okay. So -1, -3, and 4. Because if you look at the W1 row, okay, you get -4, 1, and 3. So what you get is really that you take the primal dictionary, do a negative transpose. So interchange the rows and columns and look at the negative of that quantity, and you get the dual dictionary. Okay. Yet another way of seeing this is that, remember the CS conditions associated X1 with W1, the variable in the primal problem with the slack or surplus of the other problem. So if you look at the X1, the coefficients of X1 in the green dictionary, and the coefficients of W1 and the quantities associated with W1 in the red dictionary, you see a correspondence. Okay. So the X1 column had -1, -3, and 4. The W1 row has -4, 1, and 3. Similarly, the X2 column has -4, 1, and 1, the green. So the W2 column has -1, 1, and 4. -1, -1, and 4. Okay. So the point is that if you look at the solution given by these two dictionaries, the natural solution in which the W's are set to those quantities, the Y's are 0, the X's are 0, and the S's are 1 and 3, then you satisfy the complementary slackness conditions. Okay? So these two dictionaries are complementary, meaning that you satisfy the CS conditions. So here, this is the trivial solution that you said, taking all the X's and Y's to 0. Therefore, the CS conditions are always satisfied. The difficulty is that here you don't have feasibility. Okay, so at least the initial dictionary looks like you have, you take the green dictionary, do the negative transpose, and do the obvious changes. Okay. Wherever you see X1, you would use W1, and so on. Then you get this red dictionary, and vice versa. Okay. let's actually see what happens when we pivot. Okay. So here are the dictionaries, and how would we, what does it mean for us to pivot? Let's work with the green dictionary because that's the only feasible one. The red is infeasible, so we can't do much with it. So suppose I let x3 into the basis. Okay. Suppose that's my entering variable. Of course, S2 has to leave, right? That's the only, so this would leave. And what will happen? What does the new dictionary look like? Well, S1 row is completely unaffected. So S1 is 1 minus x1 minus 4x2. Okay. The second row, I'm going to rewrite it in terms of x3. So x3 is going to be 3 minus 3x1 plus x2 minus s2. Okay? And the last row, of course, is going to become zp is, so I'll keep 4x1 and x2, and I'll use 3 times whatever I have here, okay, which is the x3 equation. And if you do that, you get 9 minus 5x1 plus 4x2 minus 3s2. Okay? So this is what you end up with after one iteration of the simplex method. Any questions about this? So this we've done it numerous times, and so we know how to do this. Now what I'd like you to do now is to write down what the red dictionary associated with this should look like. Okay. So I'm going to write it in black only, but what should it be? What is the corresponding dictionary on the right hand side? So first of all, what are going to be the basic variables associated with the red dictionary? Anyone? Okay. Notice that we want the complementary slackness conditions to be satisfied. Okay? So we want x1 times w1 equal to 0, x2 times w2 equal to 0, and x3 times w3 equal to 0. So if x3, which became basic just now, if x3 is in the basis, then what must be true of w3? W3 must be 0. So it seems like you want W3 to become a non-basic variable. Okay. So we want this to leave. Okay. And what could enter the basis? Y2. Because we know that S2 now left the basis here, so Y2 could assume any value. Okay. So it seems like Y2 should enter the basis and W3 should leave. Okay. So therefore, what should the third equation be? y2 equals 3 plus w3. Okay. Yes. So the CF conditions say that the product of y2 and s2 should be 0. Right? So just as, so the CF conditions say, if you look at the board here, it says y2 times the slack of the second constraint should be 0. And given that s2 was made 0 in the primal dictionary, y2 is free to assume any value. Okay. This is not a rigorous argument, by the way. I'm just trying to illustrate something about the relationship between these two dictionaries. Okay. So, just as the green one corresponded to the red one, there's a natural relationship between the two, we could sort of pretend that the way we went from this green dictionary to this black one, okay, we did one iteration of the simplex method. We could sort of pretend that that does something similar to the red dictionary. We just want to know what it is. So I'm just going to write down. So it will take about, so we probably have to spend another 5 to 10 minutes to finish this whole thing. Okay? So what we observed was, well, x3 is now assuming a positive value. Therefore, w3 should become non-basic. And similarly, because s2 became 0, we want y2 to become basic. Okay? Just a heuristic pattern matching that we're doing. And given that y2 has to enter the basis and w3 has to leave the basis on the, assuming that our heuristic is sort of okay, we would rewrite the third equation in this way. And once you have this, you would substitute for y2 this quantity, 3 plus w3, everywhere else. Okay? So w1 would become 5 plus y1 plus 3w3, and w2 would become minus 4 plus 4y1 minus w3. Okay? Actually, I just want to write this in a slightly different way. Let's say 3 plus w3. And of course, vd is going to be minus 9 minus y1 minus 3 w3. Okay? That's the dictionary we end up with. Now observe that the same relationship that held between the red and the green dictionaries holds between these two dictionaries. Okay? So for instance, if I look at the first column, the one involving just the constants, I have 1, 3, and 9. Here I have minus 9, minus 1, minus 3. Okay. And likewise for any other row or column. So you take the coefficients of the matrix there, you do a negative transpose, you get this one. Okay. Notice that the ZD, the last row, still has only negative coefficients. Meaning, if this were a feasible dictionary, you would stop, and this would be an optimal dictionary. Okay. But of course, your primal dictionary tells you that you're not yet at an optimal solution, and you would go on. Okay. And if you do this one more step, okay, so here, for instance, you have no choice. x2 has to enter. And if x2 enters, then s1 has to leave. Okay. So you can think of x2 entering the basis as W2 leaving in the other problem. Okay, and you can think of S1 entering the basis, S1 leaving the basis here as Y1 entering the basis there, the exact same way that we did the previous step. So if you do that, you end up with the following. Okay, so from here you end up with x2 equals 1 over 4 minus 1 over 4 x1 minus 1 over 4 s1. x3 equals 13 over 4 minus 13 over 4 x1 minus 1 over 4 s1 minus s2, and you have vd equals 10 minus 6x1. Okay. So that's what you end up with after this pivot. Okay, and if you do the corresponding pivots on the right hand side, you get w1 equals 6 plus 1 over 4 w2 plus 13 over 4 w3, y1 equals 1 plus 1 over 4 w2 plus 1 over 4 w3, and y2 equals 3 plus w3, and you have vd equals negative 10 minus 1 over 4 w2 minus 13 over 4 w3. Okay. Sorry about the sloppy writing. I'll fix it when I post the notes. So at any rate, so you can look at these dictionaries and observe that the same relationship holds, that you take the negative transpose of your primal dictionary, you get the dual dictionary with the natural association of variables on one side with the slacks on the other. Okay. Now notice, of course, that looking at the primal, you would conclude that you're at an optimal solution because everything here in the last row has a negative coefficient. And actually looking at this dictionary, you would conclude the same because you have a feasible solution now and everything has negative coefficients here. Okay. So I want you to observe two things. So what we've actually done is we look at the primal simplex method. Okay. We start with a feasible dictionary, look at what the primal simplex method does, and so that's one set of dictionaries that we have. You can think of the primal simplex method as it operates on the dual in the way we associated these dictionaries. Okay. That's the red dictionary that we started with over here. So what the primal simplex method actually does is start with the green dictionary and get to this black one. Okay. But you could also pretend that what it does is start with the green dictionary, start with the red dictionary and get to this black one. Okay. So if you sort of operate the primal simplex method on this dual problem, then it worked with an infeasible dictionary and got to another infeasible dictionary, and from there it got to yet another dictionary which happened to be feasible. All of these dictionaries satisfy the optimality conditions, so you can sort of think about this method as though it were a simplex method working with infeasible dictionaries that satisfy optimality conditions and somehow increasingly moves towards getting to a feasible point. Okay. So it's the same method operating on two different problems that gives you two different views. Okay. So we looked at what the primal simplex method does on the original problem, and we got through a series of dictionaries which are all feasible, initially suboptimal, and eventually get to a dictionary where the optimality conditions are satisfied. if you make the natural correspondence that we observe to the dual problem, the corresponding dictionaries are all infeasible. All of them always satisfy the optimality conditions, and eventually you get to a feasible dictionary. So the natural observation then is, well, why not look at a method that works with infeasible dictionaries in exactly the same way that this simplex method did on this red dictionary? Okay. That's called the dual simplex method. So there are many problems where there's a natural dictionary that's infeasible but that satisfies the optimality conditions. And in that case, you would use the dual simplex method, which is the same as saying you would take that problem, formulate its dual, apply the primal simplex method. Now, instead of actually doing all of that, you're not going to look at the dual of that problem and apply the primal simplex method. You're going to sort of do this mentally, and therefore you're designing a new method called the dual simplex method, which operates as though it were working on the dual problem and applying the primal simplex method. So in other words, what I want to do in the next lecture is to look at this dictionary and come up with a mechanism, without the part on the left. Okay, I want to focus only on this side. Start with a red dictionary and design a method that would tell me how to get to the black dictionary. That's the dual simplex method. Okay, so it's going to always have the following invariants: that the last row is always going to have negative coefficients or non-positive coefficients, so that the optimality conditions would remain satisfied. Some of the right-hand sides, which are the constants here, may be negative. So in this case, everything is negative, but some of them may be negative. So we are going to pick some variable that will leave the basis first. In this case, we would pick W3. Based on what our leaving variable is, we will figure out some entering variable such that after you do the pivot, the last row still has non-positive coefficients. Okay? So the analog is the primal simplex method always starts with something with a positive coefficient here, figures out what the entering variable is, and then once you decide the entering variable, you're going to decide what the leaving variable is so that the resulting dictionary is still feasible. Okay? So you're always going to maintain feasibility, and you're going to work towards optimality. Here, you're always going to maintain the optimality conditions, and you're going to work towards feasibility. So this is the primal simplex method. This is the dual simplex method. So I want to end with one last thing, which is that if you look at the final dictionary that you get, okay, and you look at the coefficients of the slack variables of the primal optimal dictionary. Okay. What do you have? You have -1 and -3. These are the coefficients of the two slacks. Okay. Remember that the dual optimal solution is 1, 3. y1 equals 1, y2 equals 3. That's the optimal solution. Okay. So even if you didn't have this stuff on the right-hand side, you could figure out what the dual optimal solution is by just looking at the coefficients of the slacks. And of course, this works in reverse. If you look at the coefficients of the slacks of the surplus variables here, you have W1 equal to 0, the coefficient that is. W2's coefficient is -1/4, and W3's coefficient is -13/4. Now, if you recall, that's exactly the optimal solution, right? X1 is 0, X2 is 1/4, and X3 is 13/4. This is not surprising because we know that if we have the dictionary on the left, we can reconstruct the dictionary on the right just by taking the negative transpose. Okay? This, of course, solves the dual problem. Therefore, the last row of my primal dictionary should encode the dual solution somehow. Okay? Because that row is going to become the first column of this dictionary for the dual problem. And that is the dual solution. Okay? So why do we do all of this? Well, apart from discussing the dual simplex method, I want you to I want to show you a simple proof of the strong duality theorem. Remember, the strong duality theorem says that if I have an optimal solution x to the primal problem, I have an optimal solution y to the dual problem with the same objective value. So the idea that we are going to follow is start with a primal problem. If it has an optimal solution, you can apply the simplex method and get to it. Therefore, the final dictionary is going to look like this. So what I'm going to assert in the next lecture is, I look at the last row of this final dictionary, I'm going to pull out the dual solution. And I want to show you that that solution is feasible for the dual problem and satisfies the CS conditions or has the same objective value. That will be a proof of the strong duality result. So if you recall, the very first lecture we saw that somehow it was not a coincidence that when we discussed two different representations of the same linear program, one where the solution is sort of obvious, the coefficients had the dual variables. Okay? We didn't know what the dual was at the time, but you observe that if you use the coefficients in the last row as multipliers, you could get a proof of optimality of the solution that you started with. This is the explanation of that phenomenon. Okay? So we're already over time, so I'm going to stop there and pick things up. So next lecture we are going to prove strong duality and discuss the dual simplex method and get started on sensitivity analysis. Oh, I was going to talk about the midterm. So I want the midterm to be on the 20th of October, which is a Thursday. I know that a number of you have other exams as well. So what I'd like to hear from you, I don't want to receive 50 odd emails, but if the 20th of October is extremely bad, then send me an email explaining why. And we'll see if we can move things. So the exam in general is going to be open book, open notes. I usually don't allow calculators, but maybe you can have calculators as well, so I don't mind. It'll be in class, of course, so it'll be for an hour and a half, and it'll basically test your understanding of the concepts. You wouldn't have to do involved calculations, so that's generally the style of the exam. Okay. Would I post a sample midterm? I could post a sample midterm, but you have to realize that in the past I've used take-home exams, I've used, so exams that I've used in the past may have had other rules, and therefore they may not be representative, although I'll try my best to find one that is. Okay. So I will find a sample midterm and associated solutions that you can look at. Okay. As I said, if 20th in class, so it's exactly 2 weeks from today, if that's completely undoable, let me know.
I'm taking this class for art credit. So do you think I should take the midterm?
It's up to you. I think that if